So hopefully now you have a bit of an idea of how this solving systems of linear equations through substitution kind of works. So we've gone through those consistent systems where we got an x and a y value, but we had those two other options. We had the dependent systems where the lines were actually the same line, and we had those inconsistent systems where the two lines were actually parallel lines. And so when we saw the pictures of those in 8.1, that made sense because we could see how they were different. But when we're dealing with algebra, we have different cues or clues that tell us if a system is dependent or if a system is inconsistent. And basically what we're looking for here in a dependent system, we get down to a line of truth, you know, where 3 equals 3 or 2x plus 1 equals 2x plus 1. That is my indicator that it is a dependent system with an infinite number of solutions. So solved, the solution line states that something equals itself. It's a line of truth. The inconsistent system, remembering that was the third option, is when we solve these through our algebraic approach, we get a line of garbage. So we get some nonsense here that something equals another number. So 3 equals 6 or 0 equals 2. Those are lines of garbage. It doesn't make any sense. And that is your evidence that your system is an inconsistent system. Okay, so let's see how this works. So we're using the substitution method to solve these. We've got equation 1 and equation 2. And so to solve this, I already have equation 2, solve for y. So I'm going to take that and sub it into equation 1. So where I see that y in equation 1, I'm actually going to write 2x minus 3. Remember to sub in with brackets. Oops, I forgot the 2. So solving this one, using distributive property, watch your negative signs. I'd have 4x minus 4x plus 6 equaling 6. I might collect my like terms at this point and get, 4x minus 4x, that's 0x or 0, right? That wipes itself out. And I get 6 equaling 6. That is a line of truth. That tells you that the system is dependent. There is an infinite number of solutions for this. So with these ones, they're a little weird. You need to know what to look for, but honestly, they're half the work because it's not that case of tracking down one variable and then tracking down the others. Let's take a look at this one. So we've got equation 1 and equation 2. Equation 2 is already solved for x, so it is set to be subbed into equation 1. I'm going to copy equation 1 out, replacing x with this 2y plus 2, subbing in with brackets. And then continue on copying equation 1. Now I'm going to solve my newly made equation here. I would gather up my x or my y terms, my like terms, and get 0 because it's 6y minus 6y, right? Those go away and I have 6 equaling 9. That is a line of nonsense. It's a line of garbage. And that's what tells me that this system is inconsistent. It means that these two lines would actually run parallel to each other, and there is no solution for this system. Okay, so now we have a whole page, and there is no indicator if these ones are going to be consistent, dependent, or inconsistent. So we need to know what we're looking for in each of the cases on the next page. I'm going to work through each one as we go. So I'd have equation 1 and equation 2. I'm going to take equation 2 and sub it into equation 1. Where I see the y, I'm writing out that 3x minus 2. And then I'm solving for x. I'd have some distributive property going on here. Don't forget about your negative signs. 12x minus 12x is 0x, so I'd have 8 equaling 8. That is a line of truth. You could get down to 0 equaling 0. Like if you've subtracted 8 on both sides, it doesn't matter what your line of truth is, but once you have a line of truth, not your answer either, that's your evidence that this system is dependent. It's easy to please because there's actually an infinite number of solutions. If we were to take those two lines, they might look totally different, but they actually make the same line on the graph. So we would say that that system is dependent and there's an infinite number of solutions. I'm just going to work through these ones as we work down the page here because I can see them easier. I'd have equation 1 and equation 2. And equation 2 is already solved for y, so it is primed to be substituted into equation 1. I'd copy out equation 1, replacing the y with this 2x minus 10 business. And then I can solve for x. I don't know if this is going to be one that works out easily, or if it's a line of truth or a line of garbage. Oops. When I get down to it here, I find that x equals 4. So that means that this is going to be a consistent system. I'm only halfway there. I need to now track down my other variable. So I'm going to sub into equation 2 because it was that y equals 2x minus 10, but I'm replacing that x with a 4. So I can now evaluate y as y equaling a negative 2. And so this is what tells me that my system is consistent and that I have this unique solution. I have an ordered pair of x equaling 4 and y equaling negative 2. And that would be the point where those two lines intersected. More on this page is sort of a mixed bag of stuff. Working through each one as we go. I'll do G because it's higher on the page here. I'd have equation 1 and equation 2. And equation 2 is already solved for y, so what I'm going to do is sub that into equation 1. So copying it out carefully, I'd have 8x minus 4 times y, but y is actually all of this 2x minus 4 business. And keep copying equals negative or equals 16. I'd use some distributive property first, watching your signs. At this point, I would gather up my like terms. I'd have 0x, so they would just go away. I have 16 equaling 16. If you had chosen to do other things first, you might have got down to a different line of truth. But as soon as you get a line of truth, that is your evidence that this system is dependent. It's an easy to please one. There's actually an infinite number of solutions. Those are actually the exact same line on the graph. And so I would say it's a dependent system. And there's an infinite number of solutions. A few more on the page here. We've got equation 1 and equation 2 for E. The second equation is already solved for x this time, so I'm going to take and sub that into my first equation. So I'd have 5 times this negative 3y plus 1, subbing in with brackets. Using some distributive property. Gathering up my like terms, I'd have negative 15y and positive 15y, so it'd be a 0, and I'd have 5 equaling 10 as my next equivalent equation. This is a line of garbage. This is a line of nonsense, and so that tells me that this system is inconsistent. It tells me that there is actually no solution for this system. If I were to take a look at those two lines, and they certainly don't look like it, they would actually be two parallel lines. It means that they don't come together. That this line of garbage tells me it's an inconsistent system, And from that, we know there is no solution. There's no value of x and y that actually would make both of these equations happy. So the last one here, there's definitely some work to do with this. I don't have either one of these solved for one of the variables. So I'm going to choose this second equation down here, and I'm going to solve it for x. And it might take me a couple steps to get to there. I'm going to, what'll I do? I'll start by subtracting 3y on both sides. So I get that negative x equaling negative 3y minus 1. Then dividing by negative 1 on both sides, I get my real equation 1 that I'm going to be using, that x equals 3y plus 1. That has me now all ready to take that and sub it into equation, why did I do them upside down? It doesn't matter, the other equation, which I happen to number 2 this time. Okay, so rewriting that, I'd have 4 times this 3y plus 1, and then keep going, copying this out. So negative 12y equaling 5. I'd have a little distributive property going on here. I'd have a little like terms to collect, and where I'd get a 0. So I get 4 equaling 5. That is a line of garbage. That is nonsense. It's not true. And that is my evidence that this system is, again, inconsistent. There are no solutions for it. It's impossible to please this system. You can't make both of these equations happy at the same time. There is no point on the graph where those two lines would intersect. So that does us for our first approach that is algebraic to solving these systems. The next section we're going to do is solving with the addition method, and it's another approach that is algebraic to solve these systems.